Welcome to the 89th Theoretical-Physics-Colloquium by Professor Armen Sedrakian from Frankfurt Institute for Advanced Studies and Wrocław University in Poland. He got his PhD in 1992 from Yerevan State University. He had several postdoctoral positions at the Max Planck Institute unit in Rostock University, Cornell University, and University of Groningen in the Netherlands. In 2002, he became research associate and lecturer at the University of Tübingen. And since 2007, he was at Goethe University in Frankfurt am Main. Since 2017, he is a fellow at Frankfurt Institute for Advanced Studies. And since 2018, he is the university professor at Institute for Theoretical Physics at the University of Wrocław. He is an elected foreign member of the National Academy of Sciences of Armenia since 2014. He is also an associate editor. He was an associate editor of Particles, an open access journal since 2017 for 4 years. And since last year, he is an editor-in-chief at the same journal. His research interests include physics of neutron stars and neutron star mergers, relativistic hydrodynamics, transport properties of neutron matter, cooling of neutron stars, dense matter equation of state, strange quark matter and hypernuclear matter, superconducting quark matter, axion physics, and many other things. And today he will be talking about dense QCD and compact stars. And with that, I'll give the microphone to Armen.
I will talk about dense QCD and compact stars. And actually, I will be talking mostly about compact stars and less about dense QCD. And do not expect me to talk today about deeper issues of QCD rather than I will be using simple models to predict the outcomes of QCD phase transition in the context of compact stars. So here is the plan of the talk. I will start with just setting the stage and the goals that we pursue in the studies of dense QCD. Then I briefly go on and describe the NGL models that we have been using to predict the equation of state of dense matter in compact stars, and then an approximation, which I will call synthetic parameterization, to this NGL approximation, the NGL results. Then I will just discuss mass radius diagram for compact stars and current constraints that come from astrophysics. I will go on then and discuss tidal deformabilities of compact stars and the famous GW170817 event, which is a multi-messenger gravitational wave plus electromagnetic waves event. Finally, I will talk about universal relations, and I will give you an example how one can use universal relations, so-called universal relations, to extract information about compact stars. So this work is mostly done with G.I.G. Lee, who was a postdoctoral fellow at Goethe University with me, and now he's professor in China. My longtime collaborator, Mark Alford, and universalities and their applications have been studied by a larger number of people who are mentioned here, also including David Blaschke, who is in the audience. Okay, so let me start with the first part, dense QCD from NGL models to synthetic parameterizations. The big picture is condensed in this diagram where we have the temperature on the y-axis, we have the density or baryon chemical potential on the say x-axis, and this axis is isospin asymmetry. The third axis is isospin asymmetry. So experimentally, we have information on along the low density axis from LHC, There is, and also from experiments at BNL. But this is not the region that is of interest for compact stars. We are mostly interested in the high density region of the diagram, which is covered by FAIR in the future and NICA at Dubna, FAIR at GSI. And essentially what we are interested in is mildly heated nuclear or quark matter, basically QCD matter at finite isospin. So basically neutron stars are not along the nu-b axis as sometimes it is shown. It's more important to realize that there are isospin asymmetric systems, mostly consisting of neutrons. And more recently, focus has shifted not from cold neutron stars also to neutron star mergers, shown here by this red region where you have matter heated up to 100 MeV, again dense as in neutron stars, but quite heated, and the properties of this matter is in focus of our community, especially because we now have gravitational wave information coming from binary neutron star mergers. So let me briefly mention what are the issues on the QCD side. So the QCD Lagrangian is, of course, well established. There is the quark part, which is essentially that of Dirac fields. And then we have a gauge part, which corresponds to the gluons. So psi and psi bar are the Dirac fields, and here D is just the covariant derivative. And as usual, you can express the field stress tensors through derivatives of the field itself, and then we have these last terms which are responsible for the non-abelian nature or reflect the non-abelian nature of the QCD. Now, when treating matter, well, exact solutions, as very well known, are not accessible everywhere in this diagram. And this is unfortunately also the case for the part of the diagram that corresponds to neutron stars. Large densities are prohibitive for lattice simulations, and that's why we have to rely on certain effective models. So at very high density and very high temperatures, of course, one can use first principle perturbative QCD, as well known. Unfortunately, the densities at which perturbative QCD becomes valid are about 4 times the nuclear saturation density, whereas neutron stars have central densities between 5 to 10 times the nuclear saturation density. Therefore, perturbative QCD cannot help in this matter. It can give some hints, of course, but not directly applied in the regime that we are interested in. So the gray region is where the effective field theories can be applied, and one very popular model has been the NGL model and its variants. And I will actually show and base my arguments about the equation of state of dense QCD on an NGL-like model. There are, of course, here other regions where you can apply other methods like chiral perturbation theory and at low densities lattice QCD. This is all well known. I will not concentrate on this. So an important aspect of compact stars is the possibility that you will have many interesting phases that resemble those that we know in condensed matter. And Kolar superconductors were one candidate phases, one example of candidate phases that have been discussed in the literature, and I will take that example to argue that simply treating simple one phase sort of QCD matter in compact stars may be not accurate, and once we go beyond this, there are very interesting opportunities open. So, okay, so now let's come to NGL model. This is the NGL Lagrangian. Again, we have here the free Dirac part. This is the quark mass matrix. We have vector interactions. We have a part that corresponds to scalar interactions, scalar and pseudo-scalar. So this is the usual part of the NGL Lagrangian. In neutron stars, we need this part, which is responsible for repulsive interaction between quarks. This is absolutely essential, I will show. Then here already prepared, I have a term that is responsible for pairing between quarks with some strengths, which is given by this coupling constant, and D stands for D quarks. And finally, then we have, in addition, this the Hooft interaction, which you may or may not include. It actually stiffens the equation of state. This is what we actually want to have. Therefore, we have also included this term in our Lagrangian. So I think all the notations here are self-explanatory, so I will not go into details like that. There is, we have, of course, 3 colors, and we also have 3 flavors. Other flavors are too heavy to be interesting in neutron stars. So the scalar interaction, fixing the coupling constants, the scalar interaction is as usual in NGL model is fixed to the vacuum physics, and as well as the cutoff. The D-quark coupling, if one uses the Fields transformation, then it's simply 3/4 of the scalar interaction, but this is also very often treated as a free parameter. And finally, we have 2 truly free parameters, which one of them is the vector interaction, the other is the transition density from hadronic to quark matter, since in our model deconfinement phase transition is not built in, and we have to impose this by hand. So now let me turn to the Cooper pairing in quark matter. There have been lots of papers on this topic over past 20 years, and I will just summarize the main result. What we know now is that at low densities, most likely we will have two flavor and 2-color superconducting phase, which is called 2SC phase. It has an order parameter that is proportional to these 2 Levi-Civita tensors in color and flavor spaces. One variant that of this phase arises when we have medium size strange quark mass. In that case, a crystalline phase appears, in which case essentially the gap in the spectrum of quasi-particles is modulated by some vector. And finally, if we go to asymptotically high densities, then all 3 flavors become massless and essentially democratic. And in this case, this color flavor locked phase has been considered as the most probable phase of asymptotically high density quark matter. So now let me turn to our calculations. We have included in the pairing part 2 phases, which are the 2SC and CFL phase. And sometimes I will call this as Q1 and Q2 to signify the fact that in general, what I will be talking about in the rest of the talk, it applies to any phases that, any 2 phases of quark matter which are connected by first order phase transition. This could be a quark ionic phase or some other exotic phases of quark matter. But the obvious point I want to make is that, it is very likely that QCD phase diagram has several phases, and this should be taken into account when we study compact stars. Now, there are two options to connect also the low density hadronic equation of state to the equation of state of quark matter. One is the usual one we learn in statistical physics, is the Maxwell construction, where we have a density jump at constant pressure. The other one, introduced by Norman Glendening, is proceeds via formation of mixed phase, and the difference between these two is decided by the surface tension of quark matter. For example, if we have large surface tension, which seems to be the case, usually Maxwell construction wins. Otherwise, Glendening construction should be applied. Here I will show the results when we applied Maxwell construction. These calculations are already a bit old, but to motivate my discussion, this is quite sufficient. So in the left, on the left, I show the results where we have vector interactions completely switched off. So at low density, we have a hadronic phase, and then I have several curves with several transition densities. We can focus just on one, which is 2.5 rho zero. Rho zero is the saturation density. Then we have the first jump, and then 2SC phase of quark matter sets in. And then it turns out that if you admit CFL phase, then you have a second jump, and then again here, stable CFL phase. Well, once you switch on vector interactions, in general, what happens is that the equation of states becomes stiffer, which means for a given density, the pressure is higher. But in effect, this picture that you have these two steps that lead to 2SC phase and CFL phase remain. So I will be using that argument, and I will essentially approximate the NGL model with a so-called synthetic equation of state, which has this type of construction. We have a low density nuclear part. At some energy density, we have a jump given by this delta epsilon 1. Then we have a 2SC phase. And here I will assume that we have a constant speed of sound equation of state, which means that this curve represented here is essentially a straight line. Then we have a second jump, and then we have a CFL phase, which is also represented by a straight line and constant speed of sound equation of state. Of course, the speed of sounds in these two phases can be different, and therefore the inclination of these curves need not be the same. So the model has 6 parameters. The first one defines the energy density and pressure at which we have deconfinement, then the magnitude of the first jump, then the size of the 2SC phase, then energy density and pressure at which the CFL phase starts, and then the magnitude of the second jump from 2SC to CFL phase. So we have a 6-parameter problem which approximates what we see from the NGL model. And what we would like to do is to study the implications of this type of equations of state on the structure of neutron stars. Before going to this, let me tell you something about low density hadronic equation of state. Typically in our calculations, we use density functional methods to approximate the hadronic or three hadronic phases. But a very useful approximation to representation of the equation of state of nuclear matter is the following, where you do a double Taylor expansion of energy density of nuclear matter with respect to the density. This is simply a deviation from the saturation density. You see rho minus rho zero. And the other parameter is just the magnitude of isospin asymmetry, which is you see here the difference between densities of neutrons and protons divided by the total density. So if you do the Taylor expansion, you have this form which is fixed. It's obviously there is no room for modeling here. The only we have only to fix from experiments or theory the coefficient of this expansion. It turns out that the low order coefficients of the low order terms are very well fixed. And the most interesting parameters that are now under study are this symmetry energy, which is also, quite tightly fixed around this value. And less fixed is the slope of the symmetry energy, this L parameter. And when studying variations in the nucleonic equation of state, we will be mostly considering the effects of L, since it turns out that L is strongly correlated with some important properties of compact stars. Here I have a plot taken from Latimer and collaborators, where we have here the symmetry energy and its slope, and here we have information coming from different different parts of nuclear physics, including heavy ion collisions experiment, for example, modeling heavy ion collisions, giant dipole resonance here, light green, and so on. So so remember the numbers that essentially the region that that is covered by most of these areas is around 60, between 40 and 60 mega electron volt. There was a recent experiment by PREX-2, essentially PREX-2 experiment, which measured the surface skin of lead, and one of the analyses came up with a very large value of L, which was around 105, so somewhere here. And actually the symmetry energy was also quite large, 38 MeV, so it was somewhere here. So many of us were puzzled and looked also into the possibility of having neutron stars, which in the case where L and S are far off from the average values that we are used to. Yes, and now here I have some of our equations of state, and the uncertainties are very easily, as you can see, low density uncertainties, you see this band, are very easily accounted for if you just simply vary L symmetry. If you construct your density functional, and this is possible, that's so that the L is varied, and this value of QSAT is also varied. That's responsible for the changes in the high density region of the equation of state of nuclear matter. This much about nuclear matter, and let's go and see what we find having all this phenomenology under control. So stationary compact stars, static compact stars are the solutions of Einstein's equations in spherical symmetry, which are given by this famous Tolman-Oppenheimer-Volkov equations. Essentially, the input is here pressure as a function of energy density, then it's simple integration from the center of the star towards the surface in spherical symmetry, and then we obtain the masses of the stars for any given equation of state and the radius. Here I have given some examples of density functional theories that provide radii and masses of neutron stars. An important aspect is that for any equation of state, we always have some maximum mass. So at some point, these curves reach the maximum and then they go down. And it is also known that once the turning point is passed, the stars are unstable. So essentially only these part up to the maximum, the sequences correspond to stable stars. Otherwise, they are unstable. Now, astrophysics allows us to measure the masses of neutron stars. Here we have names of the pulsars, and on the y-axis are the masses of the pulsars, and they are arranged so that from left to the right, the masses are increasing. And as you can see, most of them, here is a histogram, most of them are located around 1.4 solar masses, and this corresponds to so-called canonical neutron stars. But there are also stars that are located at the upper end, around, you see, 2 solar masses, above 2 solar mass pulsars. And this is, of course, very important in the context of the previous figure. Sorry. So previous figure where you see there is a maximum. So essentially, if you have an equation of state that lies below 2 solar masses, these values that are colored, the equation of state cannot correspond to real, to nature, to real compact stars. So this allows us to place already strong constraints on the equation of state of neutron stars. Now, let me come to the families of compact stars. Generally, this is a picture taken from a classic book of Shapiro-Tukolsky, Black Holes, White Dwarfs, and Neutron Stars, which was written in the 80s. So you see that there are several families of compact stars. So if the central density, this is x-axis is the central density, this is the mass in solar units. So if you take very low central densities, you end up having white dwarfs, and the increasing branch is stable. Then you have an instability region between points A and B, and then neutron stars come in between points B and C, and then you have again an instability region. So it was then proposed in 1968 that there could be a separate branch because of onset of quark matter and first order phase transition, first by Gerlach, and much attention this problem of third family, because this is the first, second, and this is the third family. Third family started when Glendinning rediscovered essentially this issue, and together also with Fridolin Weber, they started looking at the properties of this third family of compact stars. So recently we have found in this paper that there could be yet another family of compact stars if you allow for a phase transition in QCD phase diagram. So again, we use this construct. I explained it before. It's actually an extension or generalization of the work by Alford, Han, and Prakash, who considered simply two phases and postulated that the quark matter equation of state can be approximated by this constant speed of sound, CSS parameterization. So essentially what we did is to add yet another phase on top of what they have done. Now, okay, this is just the analytical form. Once more to remind you what are the parameters in our equation of state. Pressure at which the confinement sets in, the speed of sounds in the two phases, and they are generally different, obviously. And then we have these jumps in the energy density at each transition. So now let's come to the results. Here, what I'm showing is the central pressure. You can think also of central density, but here we show the central pressure as the function, and on the y-axis we have the masses of the stars. So at low pressures, you have hadronic stars, so essentially hadronic stars. At some point, once the transition sets in, we have instability region because the curve is going down, but then stability is regained for a certain parameter range, and then you see, depending on the magnitude of the second jump, which is normalized by first jump, we have here a family of stars. This is done especially, I mean, you can have also family here, but here is to show what are the options of this new fourth family of compact stars, because this is our second family, third family, and this would be the fourth family of compact stars. So here are the parameters for which we obtain different, these curves. And the interesting feature is, of course, here that you have an instability region again. and you regain stability. And this is absolutely and only because of the second phase transition in quark matter to the CFL phase. Another interesting feature of this curve is that triplets of stars appear, and triplets are those stars which have the same mass. Imagine drawing a straight line along this line. Then you have three branches, 1, 2, and say 3, and three stars which have same mass, but they have different radii. The same thing, this is now replacing the central pressure by the radius. Since masses and radii of compact stars can be measured, you essentially can put here some constraints coming from these measurements, which I will show later. Again, we have here hadronic stars with 13 kilometer radii, then instability region, the second branch, and then you have the third branch of stars, which are much more compact. The radii are around 11.5 kilometers. And now here I have also drawn essentially the density distribution inside the stars. The three stars, so this is completely hadronic star. This is a star with hadronic matter and 2sc phase, and then hadronic matter, 2sc and CFL phase. All these three stars in physics essentially have the same masses. So in the computation, which is given here, they have different radii, but they are triplets, of course, because they have same masses. And the radii, you see that the smallest triplet is very compact and has a CFL phase in the center. The next one is the less compact hybrid star, which has 2sc phase and then the hadronic phase. And the radii are actually computed. This is not an illustration. The radii that you see are actually computed values for our parameter set. Now we can analyze also the stability with respect to the magnitude of the jumps, the first jump and the second jump. And it turns out that if you have small jumps, the two branches are essentially stable. So this is SS means stable, stable. Both branches are stable. But then if you increase the magnitude of the jump, then you have instability regions where you have unstable, stable, and then stable, and so on. The case where you have unstable, stable, unstable, stable leads naturally to triplets, because this is what you see here, that you have stable, unstable, stable, unstable. So then you have triplets, and so on. And if the jumps are very large, then you have a complete instability region. So there are no stable stars. Now let's come to the tidal deformabilities and radii of compact stars. And let me start with GW170817 event. This was the first observation of binary neutron star in spiral in gravitational waves. What you see on the y-axis is the amplitude of the gravitational wave. The point where stars contact each other is chosen to be time equals 0. So this is the pre-merger phase, and this is the post-merger phase, and so-called ring down. So what has been observed is the pre-merger phase, and here is just an example of taken from simulations to show you that we are dealing with highly dense matter. Here is the density. So in the centers, we have essentially densities far beyond the nuclear saturation density. But what is most interesting here is that the event was not far away, around 4 megaparsecs away, and there were a lot of electromagnetic observations of the same event. There were gamma ray burst. Gamma ray burst was seen 2 seconds past this merger. There was an optical source, infrared emission, ultraviolet, X-rays, and radio waves. So essentially, the whole electromagnetic spectrum was observed in this event. So yeah, here are some snapshots from the simulations. So here we have 2 stars which are separated, well separated, but you already see that they are not spherical because the tidal field of one star deforms the other star. And here you see the tidal deformation very strong. Essentially, these are already not spheres, but ellipsoids. And then after merger, you have this post-merger phase, and eventually, most probably, a black hole is formed here. So the characteristics that can be extracted from these gravitational waves is actually a quantity that is called tidal deformability. It's the coefficient that connects the tensor of tidal fields of the companion to the quadrupole moment. So this is essentially tidal deformability, and sometimes or often one uses this dimensionless tidal deformability, large lambda, capital lambda, which is lambda divided by m to the 5. And here we have the results from the discovery paper where 2 tidal deformabilities of 2 stars are shown, and then we have the 50% and 90% credibility intervals and results for a number of equations of state. And you see that some equations of state are outside of 90, essentially 2 sigma result, which immediately excludes these equations of state from consideration. Some known results here from Monte Carlo and Skierm and relativistic Dirac-Bruckner, there are within this range, and they are fine. They can be accepted. Another type of observation that was revolutionary in this field was given by the NICER experiment, which is observing hotspots on the surfaces of neutron stars, and from the modulation and fluxes that in X-rays that come to us, and modeling them using different configurations of hotspots, it was possible to deduce masses and radii of 2 pulsars. One of them is a canonical mass star, 1.34 essentially, and it was deduced that the radius is around between 12 and 13 kilometers. And the other one, so these are 2 different modeling. One is by a group in Amsterdam, the other in Maryland, US. And then we have a very heavy star, actually the heaviest star we know, JO740, which has the mass above 2 solar masses. And the striking, result, and which was very surprising to many of us, is that the radii are almost the same. So there is no big difference between the masses of canonical mass, the radii of canonical mass stars and most massive stars we know. Now let's look what these constraints predict for mass radius diagram. Now these violet ellipses are 2 sigma constraints coming from NICER. Result for canonical mass star. Here is its number 0030 plus something, and then we have this heaviest neutron star JO740 plus something. We have again this 2 sigma result, and the yellow band that you see here is the constraint that comes from GW170817 and tidal deformabilities that were deduced and then transformed into mass radius diagram. And then you see that we have significant constraints on the radii and masses simultaneously. Now I have here a modeling of hadronic equation of state where when this modeling is mapped on this Taylor expansion, and what is varied is this L parameter between 105, which was deduced from T-Rex2 experiment, and 45, which is a typical lower value of typical range. And you see that, for example, if we look at these reddish curves, changing L changes the properties of stars, or covers the large range and changes the properties of stars at low masses. Now, if we here, I have three families of stars with different Q values, -500, -100, and 900, and you see that the maximum masses are changing of the stars once you change these parameters. They do not affect essentially changing. They do not affect essentially the radii of the stars. Okay, so this is if we have just hadronic stars, but now let's look what is happening if we have phase transition to quark matter. And here is an example where we have hadronic branch, and then we have an instability, and then we have quark phase. And essentially different colors means that the transition occurs at different density. Consequently, the maximum mass on the hadronic branch is changing. So, and what we see that this late transition to quark matter is inacceptable in terms of GW 170817, since in this case we need the curves to pass through this region. And once we have low density phase transition, then we are okay with the gravitational waves, and we essentially also cover the nicer results. An interesting feature that is shown here in the inset that we have twins. We have stars with the same masses. So if you draw a horizontal line, you have stars on the nucleonic branch and you have stars on the quark branch, which have same masses but different radii. Now, the same picture, if we have triplets and we have two phase transitions, the arguments are very similar. You have an additional phase in between here, and then this is our CFL phase, essentially. And here you see a similar situation that you have now triplets. So if you draw a straight line, you have hadronic, 2SC featuring, and 2SC plus CFL featuring stars, all having same masses but different radii. This has implications, because if in the future we observe stars with same masses but different radii, this will be immediately a signal that we have a first order phase transition, most likely to QCD. I mean, we have
Armen?
no other. Yes.
We have a question from the audience.
Yeah.
Henry, go ahead.
Yeah.
Hi. One question on the slide that you showed with the hotspot models.
Yes.
Hotspot derivations. It looked like on the second one, on the lower right there, you have a higher mass, but a larger radius. You would expect the radius to be smaller the higher the mass. One does seem, the one in the red looks smaller, which you would expect, and the one on the right, the blue one with 2.07 mass, has a larger radius. Kind of interesting. Can you explain that, please?
Yes, sure. I mean, first of all, if we look at mass radius curves, let me pick up one of them. Actually, it's the best is here. You see that you know, mass radius relation is not trivial. You know, you can have you know, higher masses, larger radii. If you compare like one solar mass star for this equation of state has 13 kilometers, you go up 1.5, it has a larger radius. So this is effects of general relativity. This is not really trivial. You know, there is no trivial relation between these. Another answer also, you should pay attention also to the error bars. So so here, you know, the result for masses are, you know, I think within other error bars, they agree. Actually, the mass, the second mass is measured much more accurately from radio observations, not from X-ray observations. So I think this was sort of constrained already from radio observations.
Okay, interesting.
Okay.
Appreciate
Yeah.
it.
Yeah. Now let's come to the deformabilities, because we have observations here. Again, this is 1 sigma result. This is 2 sigma result. And now we have many curves here, and I have to explain this. So first we have hadronic pairs. And these are shown by solid lines and marked by Latin unity. So you see that they are completely outside of the 2 sigma result, which tells us that our equations of state are actually too hard to explain the data. But once we include a phase transition, of course, here is something that I don't want to talk, but if you include delta resonances in the system, then you can bring also the tidal deformabilities down without transition to QCD matter. But let's concentrate on phase transitions and QCD matter. Then you see that there are stars which have the second phase, CFL phase, and hadronic phase. These are located here, and some of them are okay with 2 sigma results. And the best is that when you have 2 hadronic, 2 hybrid stars, 2 stars with phase transition, then you are perfectly okay, and you are quite well in the 2 sigma confidence interval. So essentially, you see that the conclusion is that if you have a phase transition, then the tension between purely hadronic equations of state and the observations is completely relaxed. Here we had different masses of stars. Here we fix the mass. We consider only equal mass stars, which are 1.36 given by experiment. In the case in the merger, we had 2 equal mass stars. We don't know really. Then you have this situation, and again, when you have 2 stars which both have quark phases, then everything is fine. If you have hadronic only stars, then you are outside of the confidence interval coming from the experiments. Now, if we include 2 phase transitions, the situation is even more complicated, because we have, in general, many more types of pairs. Here you see you can have pairs where, for example, one star has just single phase, the other has 2 phases. This would be Q1, Q2, and this one is with 2 phases. But from the experimental point of view, the situation is the same as with single phase transition, which is to say that if you have a phase transition to quark matter, then the tension that is present when you have hadronic stars is relaxed, and then you have you have perfectly well-behaved stars from the point of view of gravitational waves. Okay, so let me come to my final point, which is the universal relations and their applications. So universal relations are relations among certain global integral parameters of neutron stars. And they present some mystery because we don't have a clear understanding of underlying physics, why they exist, why these relations are there. They were established phenomenologically just by, doing sort of a numerical experiment and proving it, but essentially their deep physical underpinning is not understood. The point is the following, that independent of which equation of state we take, it turns out that the relation between moment of inertia and the love number, which is essentially tidal deformability, or moment of inertia and quadrupole moment of a star, are the same. They are completely independent of the equation of state. I will show examples in a moment. So this work was started strongly by Yagi and Younes, although there were hints in the literature going back 20 years, and after that lots of people took this over. So first this was described for zero temperature and slowly rotating stars, then it was established also for rapidly rotating cold stars, magnetized cold stars. I started contributing with finite temperatures stars, and we have also did some other applications. So this is the literature. Perhaps you can look at different universalities later, but I will not go into detail. Here is a work done also with David Plaschke, who is present, and Alvarez Castillo, where we have different equations of states supplied by myself and the gentleman I mentioned. Here you have single phase transition pressure as a function of energy density. With this input, we compute the moment of inertia, which is normalized. This bar means that it's normalized by a mass, so in a convenient way. And here you see different equations of state, and you see that the relation between moment of inertia and tidal deformability is independent of equation of state. So that's why we call it universal. The deviations are shown here. You see they are at the order of percent. So 1-2% deviations here. Here we have the same for quadrupole moment, and quadrupole moment you can generate if the star is rotating. And here we have different rotation rates. Independent of rotation rates, we see that this equation of states of hybrid stars obey strongly the universality. Okay, here are more examples where I have a recent paper with my Wrocław colleagues. Here we have hadronic stars. Now we have a different universality, a universality between maximum mass of rotating star versus the maximum mass of non-rotating star. And you see that, taking different equations of state provides also universality. Here we have the same for a big collection of equation of state which have phase transition in the star's interior, and again we have a universal relation. There are more universal relations, but let me come to the application, because the interesting physics comes in when you try to apply this to some concrete scenarios. And this was applied to GW 170817 to deduce, to put effectively a maximum a limit on the maximum mass of a static neutron star. This is given here, m 12. So, and the idea is the following, that what we know is that at the moment of the merger, a star is formed which is 2.7 solar masses and definitively too heavy to survive. And the idea, further idea, is that initially this star is differentially rotating, but because of friction and shear effects, it quickly goes into a mode where it is rotating uniformly. And uniformly rapidly rotating star sequences are located along this line. And they are completely supported by rotation. And this line would be the line where we have static stars. Now, the idea is that a hypermassive neutron star is formed. It follows the evolution. It comes to or it ends up around the maximum mass of supramassive sequence, which is rapidly rotating. And then after 10 milliseconds, it collapses to a black hole. Now, what we can learn from here, it turns out that in principle, you can place a limit on the maximum mass of this star. And the extraction is very simple. It makes use or simply makes use of conservation of baryonic mass. So what you do, you equate the masses of your system at t equals 0. That's the moment where the hypermassive star is born. and the moment where the star collapses. So initially you have a star with baryonic mass at at collapse. So you have some entropy, and then you have some electron fractions. So these are needed to characterize the equation of state. And then afterwards, you have some losses. There are mass losses to ejection and outburst. And then you have the final mass, which will collapse to the star. So this is our initial equation, which just simply tells you that the baryonic mass at these 2 points of time are equal. Baryonic, usually we are computing the gravitational mass from the equation of states, and then baryonic mass is related to gravitational mass with some coefficient, which is typically 1.2. Okay, now instead of now we have this hot star, which is here the gravitational mass, which we can compute, and then we make the assumption that this is a Keplerian star and it's at the maximum. So at that point, I'm making an assumption that we are not somewhere in this region, but exactly at the maximum of a rapidly rotating sequence. So Shibata et al. Have relaxed this assumption and show that this is not very essential. Now we can solve this equation, simply this equation for this Keplerian mass, which gives me this equation. I know M0 from experiment. This is also can be estimated. These are small corrections. So essentially what remains is to estimate these 2 etas. One is for hot stars and one is for cold stars. So it turns out that universality breaks down when you when you compare hot stars, hot rapidly rotating stars to cold stars, as here shown as a function of entropy. If you do the same for hot stars, Keplerian stars versus static stars, then you have universality fixed. All the equation of states give the same curves. Whereas here, if you normalize the hot star onto the cold star, then the universality is broken. Now we can compute this eta parameter for various equations of state. These are all listed here. So, and you see that essentially they follow the same line. For any given mass, I can always extract this eta parameter. So that's good, because then I can insert in my equation the eta parameter both for cold and hot stars. And then the right-hand side is essentially known. That's what we are doing. So M0 is given by the experiment GW170817. This is very well measured quantity. So this is known. Ejecta and outburst masses can be estimated from the optical and X-ray and other electromagnetic observation and modeling of kilonovae. So we approximately know this quantity. So the masses of the stars that participated in this event are also known. So once we know the masses, we can go back. You know the mass, you can read off the eta parameter in the mass range that you are interested. Then for cold stars, we have these values around between 1.6, 1.2. That's the limit we have. And then we have these two numbers, and then you can adopt a certain number for this. And then you can compute the same eta parameter for hot stars, which are given quoted here. And then once you substitute these values, the whole right-hand side of our equation is known. Then we obtain immediately the Keplerian mass of a hot star, and this is interesting. So assuming different values of entropy, we have 2 values of stars, hot stars, which are quite close. And it's very interesting with very few assumptions, we are able to deduce the Keplerian mass of a hot star. Finally, we can use universality to compute the static masses of hot stars. These are the results for 2 different entropies, 2 and 3. But then the universality is broken, and I cannot go trivially from hot stars to Tolman-Oppenheimer stars. But again, if you assume certain relations, which can be deduced from the computations, then we have an upper limit on the Oppenheimer-Volkoff masses of stars from this very simple analysis. And it turns out that you saw the results for J0740. The mass was 2.08, and this upper limit is very close to what is observed. So we are probably already observing pulsars that are very close to their maximum mass. So our work essentially showed that one should take into account finite temperature equation of state in order to place a correct Tolman-Oppenheimer-Volkoff limits. All previous workers, which are listed here, always used cold equations of state and cold universality relations, which, as we showed, break down, and then the whole argument doesn't work as good as one expects, but still it's very interesting that universalities can be used to extract limits on masses of compact stars. Okay, with this, I would like to thank you for your attention and open the session for questions. Thank you.
Thank you very much for a nice presentation, Armen. We do have at least one raised hand now. So Oleg, please go ahead.
Well, thanks for interesting talk. And I have a question concerning universality. And
Yes.
Is it possible to have any relation for black hole with black hole universality, like no-hair theorem? In particular, is it possible to compare the entropy to the black hole entropy, or maybe some other possibilities?
Yes, actually, the pioneers Yagi and Yunus are coming from black hole communities, so they moved then into neutron stars and brought this universality ideas. So yes, in the case of black holes, also you have certain universalities.
Yeah.
However, finite temperature issues and entropy, I'm not sure if this can be transferred to that case, because in our case, entropy is not, the Hawking effect, but this is real entropy of real, particle gas. These are probably different. Well, maybe, that the other one is related to the area and things like that. Here we have just statistical ensemble that is at certain temperature and has certain entropy. This is more usual stuff rather than you find in black holes. But you are right.
Maybe it's still possible to compare. But
yes, maybe, maybe, yes.
Okay, interesting. Okay, thanks.
Yeah.
Okay, next question, David Boschke, please.
Yeah, hello. So I have a good message and a bad message concerning the force family of these stars. The good message is that we have made many studies of NGL type models for quark matter and neutron stars with also non-local generalizations. And what we find is that indeed the quark matter has a behavior where the speed of sound is rather constant. But that message is that the range of speed of sound squared is very much around 0.5. And what we have seen in Armen's talk, and this is now my question to Armen, is that one needs a bit higher values of the speed of sound squared, a bit closer to the speed of light, as far as I remember these works. Right. And my question to Armen is whether he has an idea how to save this otherwise very nice scenario. How realistic is the synthetic equation of state that you presented?
Well, you are certainly right that asymptotically speed of sound tends to 1/3 to conformal limit, and so
I was now speaking about 1/2. So we have the good message is it is indeed larger than 1/3 in this non-perturbative domain, just at the transition. and also rather constant, like a constant speed of sound model seems to be a really good model for a more or less non-perturbative model like a NGL or non-local NGL. But to reach values, let's say above 2/3 or more closer to 1, which somehow in this scenario which you showed is necessary to have enough stiffening to then have a 4th or even 5th family. That is there some idea? So we found values, let's say up to 0.6, but not much higher.
Yeah. So you have vector interactions?
Yes, of course. Yeah.
Yeah. So, but then you know how you limit their strengths. So you have to limit their strengths from above in order to keep the equation of state soft, or below the value 1/2. I mean, if I crank up vector interactions, I will end up at some point with very large speed of sound. Nothing prohibits you having strong vector interactions, unless you have some arguments, you know, symmetries or whatever.
That would be your suggestion, but then one has to check how whether also this is rather constant. Okay, so that's your views.
Yeah, vector interactions are
crank up vector interactions.
Yeah.
Okay.
But this somehow just okay. That's the last remarks, but then you need also to scale up the dark quark interaction in order to have a more or less relevant early phase transition onset. You said you also show that it is helps not much when you have the phase transition and close to the maximum mass. You want to have it around 1.4 to fulfill the tidal deformability.
Yeah, that's more a new insight from after GW170817. It's clear that you have to have a relatively low transition. Yes,
and everything boils down very much to speeds of sound of around 0.5. So speed of sound squared.
Yeah.
Okay, let's move on to the next question. It's from Jose Jimenez. I hope I pronounced that correctly.
Yes, it's pronounced correctly. Thanks. Thank you, Professor Armen, for your presentation.
You're welcome. Yeah.
I just have two curiosities. The first one is related about the stellar formation of these high-burst neutron stars with 2 sequential phase transitions. Maybe you have some insights about this formation. And the second question is that if sequential phase transitions implies the existence of 2 critical endpoints in the fine temperature limit.
Okay. Well, let me answer the first question. So yes, that's a question that I get every time. Probably I speak about this, because people are. The question is how you form those stars with you know, which are more compact. If you are starting with a star which is, or a proton neutron star which is you know, which is relatively dilute, and how you go beyond the first maximum, because but my answer would be is that this is a dynamical process, and unless you do a simulation of the collapse and study different parameter sets, you will never know whether you know, the dynamics will push the star. Will essentially, you have to create local regions of very dense matter, so that in that regions you will create a CFL seed, and then the star settles in a different you know, in a different minimum. You should imagine that you have several minima in your end as an end outcome of your dynamical process, and then you are starting with some initial conditions, and you are looking at the collapse and seeing in which of the minima the star ends. If the numerical experiments show that you always end up in the hadronic star, then I will say, okay, there is we have to think about other ways of you know, creating. That's about isolated stars, but also we have lots of stars that are in binaries and accreting matter. So you can have initially a hadronic star, but through accretion, it you know, its mass becomes larger, and then you can push it over the stability point, and then you can populate the other, branch. Actually, I know that I haven't seen any published results, but our numerical relativity colleagues tried to put a star on the unstable branch between the hybrid branch and the hadronic branch and perturb it from the equilibrium and look in which direction the star will go. So there are already some experiments to understand what is the dynamics, but there is no answer from static point of view. You have to really do the dynamics and see what is the outcome. Okay, and the second question about critical endpoint. Yeah, I mean, yeah, I don't have insights on this. I can't a priori tell you how the phase diagram will look at finite temperature. Actually, Igor might know even better because he has done like 15 years ago the phase diagram of these phases at finite temperature.
I don't know if there are any universal relations that would tell you immediately that there should be several tri-critical points. I believe that was the question.
Well, actually, I can definitively tell that you can have a tri-critical point between, if you allow for these crystalline phases along with 2s phase allow. This is established also in cold atoms and nuclear physics. You always find tri-critical Lifshitz points in these systems. So once you allow for different phases, you have a huge richness of of all the things that you usually find in condensed matter physics. So I'm not sure there will be two endpoints, but definitively there could be another critical or tri-critical point that arises just because you consider in more detail the phase diagram of quark matter. Okay.
Right.
Thank you.
So. Thank you. Yeah, and any other questions? There were several comments in the chat room, so I suppose we could give the floor to Oleg, who may want to add some comment to that.
Well, thanks. It's just some addition to what I said already. Because indeed, it's possible to get some notions and some quantities which appears in gravity, like Hawking-Unruh temperature and conical singularity. So it's possible to get in statistical physics. And maybe I never knew about such universality for neutron stars, and it would be very interesting to indeed to have some very macroscopic manifestations of such similarities. So this is what I wanted to.
Okay, thank you. Thank you.
I think it is a fair comment. Yeah. Anyway, there is another reference in the chat for those interested regarding the universality relations. So I suppose please use that chat window to see the reference. If there are any other comments, please raise the hand if you want, or questions, and you will have a chance to ask it here.
Can we show slide 28?
Yes.
The person reading the question here.
Just
20, I think 28 here.
This is 28.
Yes.
No, Indiana, talked about Indiana before. Oh, here, Indiana food. And comes from Notre Dame there. Which group is it? Which university?
Oh, that's the group of Chuck Horowitz. Chuck Horowitz. Bloomington, Indiana.
In the south here, right? Okay.
Well, I don't know the geography.
Oh, well, I know it. The landscape's beautiful in Indiana, but okay, thank you.
Yeah, it's in Bloomington.
Okay. He is in Bloomington. So anyway, any other questions before we start wrapping this up? Let me see. I actually probably had some questions on my own, but some of them have been already addressed. Yes, there was this sort of generic representation of the nuclear equation of states somewhere, I suppose,
Yes,
around page 10 or so, where you showed the energy density, but not the pressure. I forgot, frankly, do you have another set of similar parameters for the pressure as a function of the same parameters? So is it all of these parameters that you have here, or basically there is twice as many because there is a similar relation for the pressure?
No. This once you fix these parameters, you fix essentially the thermodynamics, so you can get the pressure without.
Yeah, that's exactly where my confusion is. I forgot exactly. How do you extract pressure then? You still need pressure for Tov equation.
Oh, exactly. Yeah, that's true. Essentially, what you have to do in order to have an equation like this, or you know, you have to have a model. So essentially, you have to have a density functional. So we have these relativistic density functionals which predict all the values here, or some of them are fitted actually in the density functional, but they predict these values. And you know, and actually yeah, I mean, maybe I go in too much detail, but in our density functionals, we can change the density dependence of these parameters. So then, you know, then you can change these parameters by changing the density dependence in your density functional. I don't know if this makes sense to you, but essentially, you know, once you fix these parameters, you are fixing essentially Lagrangian. So if you change this parameter, you can change your Lagrangian. And once you change with new Lagrangian, you can again compute the pressure. So okay,
that's fine. I understand what you're saying. Essentially, you're saying that there should be a specific model behind. This is not the model. This is just the parameterization of the energy density.
Yes.
I see. Okay, it's fine. I thought so, but frankly, I got confused because I thought maybe you have a universal equation of state, then just parameterize with those 5 parameters, and that's it. But that's not the case. Okay, that's fine. Okay. I guess this is. Oh, and there is one more question. Unfortunately, I didn't record the slide number where you were showing the universal relations between the masses of rotating and non-rotating stars. On that slide, there were actually, it didn't seem to be universal because there were 2 lines, not 1 line, and I got confused, didn't catch quickly enough why there were 2 lines if it's a universal relation.
Okay, just a second. So you mean
a little further down, it was the masses, not the moment of inertia, masses on the left.
Yeah.
You have 2 different lines, not 1 line.
Yeah, here I think one is the temperature equals 0, so these are cold stars, and the other is finite temperature with fixed entropy. So
essentially, if you change the entropy, the universality changes. That's the claim.
Yeah.
Okay.
Yeah.
So it's not quite universal in that sense. It depends on the temperature.
Well, you see, the point is that one of our main contributions was that to look at isoentropic stars, because if you keep temperature constant, you don't get universality at all. So some people were previously claiming that universality breaks down if you go to finite temperature. What we've shown that it's not true. You have to go to isentropic stars, and in that case, universality is maintained.
I see.
Okay, so it's a bit tricky.
Okay, that clarifies. Thank you. Yeah. Okay, I don't see any other questions, raised hands. So we'll use this opportunity to thank Armen again for a nice presentation. And with that, we'll wrap up the official part.